All right, folks, last video here for Unit 1. So we talked about linear functions. So what we're going to do in this last section is something that you guys learned a long time ago, and we are actually going to solve linear equations. So as we start talking throughout the year about the different types of functions, we're also going to go into actually solving them. So solving them is the more applicable thing to real life, that we're trying to find what are called solutions, and this can be applied to any given situation in a real life sense, where linear functions can be used. So the key thing here is that we're going to be solving what are called mathematical equations. So first of all, an equation, just so we can get our vocabulary straight, is when you see this equal sign being used. And essentially what it's saying is that these two mathematical expressions, an expression is what you have on either side. So here I have 2x plus 4 and I have the number 12. Those are called expressions. So an equation is just a statement where I'm taking two expressions and saying that they are equal. Okay, so I'm saying that 2x plus 4 equals 12. So the idea here is that whatever x is, I'm trying to figure out what that value of x would be, such that this side right here, the 2x plus 4, should give me 12, so that in the end, I have a statement that says 12 equals 12, which is the definition of things being equal. They are the same. So our goal for this is we're going to try and solve these things. Now to do this, we're going to use what are called properties of equality. So it says that if at all any two things are equal, so if A equals B, if two things are equal, whatever I do to one side of an equation and whatever I do to an expression on one side, I have to do that same thing to the other side. So let's take, for example, I have two numbers. Let's say I have 3 equals 3. Those are one number. Let's say that I take a number that's equal to itself. What this property of equality says is that let's say that I take another number, let's call it C, and let's say I add that to one side. So let's say I take and add C. So let's choose a number, let's say 2. Let's say I add 2 here to give me 5. Well, 5 is no longer equal to 3. If I want these things to stay equal, what I need to do is I need to make sure I add that same thing to the other side. So I need to add 3 over here to make sure that no matter what I do, they always stay equal. So whatever I do to one side of the equation, I have to do to the other. I can do this same thing with subtraction. Say I were to subtract 2 from both sides. Well, if I subtract 2 from both sides, notice in the end, I still get an equality statement where I get two numbers that are still equal to each other. I can apply this to multiplication. So if I have 3 equals 3, and let's say that instead of adding or subtracting, let's say I multiply by 2. Well, if I multiply by 2 again, I'm going to get 6. So in order to make sure that stays equal, I have to multiply the other side by 2 so that in the end, I still get an equal statement of 6 equals 6. And then the same thing is true if I do division. Okay, so if I take 3 equals 3, and let's say that I'm going to divide this, I'll divide this by 2. So 3 divided by 2 is going to give you 1.5. I'll just write this as a decimal. So if I want to get 1.5 on the other side, well, guess what? I need to divide that 3 by 2 as well to also get 1.5. So no matter what I do to one side of an equation, I have to do to the other. Now, that property of equality, that's going to be our process on solving things. Our goal when we solve an equation is to try and get the variable that we're trying to figure out, whether it's x, whether it's y, whether it's whatever letter we want to use. Our goal is to try and isolate that value to try and figure out what that thing is. Again, we're trying to figure out what that value of the variable is so that the equation remains true. So the best way to do this is if we get complicated equations, like for example, if I get 2x plus 4 equals 10, my goal is to try and figure out what the heck does x need to equal such that I get 10. So one easy way to do this is, especially as we get to more complicated equations, is instead of trying to think through this problem, we can use what are called inverse operations. Inverse operations are doing the opposite to whatever we're doing or whatever we see at the beginning. So if I see 2x plus 4, first that means I'm adding 4. Okay, so I'm adding 4, which means if I want to do the opposite, I want to subtract 4. Okay, when I see the 2x, this technically means that I'm multiplying by 2. So I want to do the opposite. which is divide. So inverse operations are going to end up allowing me to solve, and no matter what I'm doing in these equations, my goal is to always find the solution. I want to figure out what is that value that makes that equation true. What would be the value I would, in the end, plug in for x in order to get 10 equals 10. And that is our goal here, using some of the tricks and trades we've learned up to this point. All right, so let's start off with some simple equations here. So let's say I have x plus 2 equals 6. Now, some of you can probably think through this right away, and some of you will know the answer, what x is going to equal. But our goal is to find a solution. So what value of x would I plug in there to give me 6? So what plus 2 would give me 6? That's kind of the thought process. To show you inverse operations, a lot of folks like to draw that line down the equal sign because we're going to split up those two expressions. Inverse operations means this: if I see x plus 2, I'm going to subtract 2 because they're opposite. On the left side, that ends up canceling each other out. 2 and negative 2, by doing the inverse, cancels out, which leaves me with just x. And that's why we do inverse operations, because they're going to undo each other. And on the right side, they don't cancel, but they combine. 6 minus 2 gives me 4. So I know then that my solution is 4. And again, that's the solution because what does 4 plus 2 equal? Well, 4 plus 2 equals 6, so that makes that statement true. All right, next one, if I have then 2x minus 1 equals 9, a little bit more here. Now I have multiple things, so here's my line. I have on the left side, I'm trying to solve for x, but I have 2x minus 1. So that means I'm subtracting 1 and multiplying by 2. So to solve this, what I'm going to do is do my inverse operations. So where I see minus 1, the opposite would be plus 1. It's going to cancel on the left side because negative 1 plus 1 cancels each other out. And on the right side, they're going to combine to give me 10. Now lastly, 2x equals 10. To solve for x, again, I want to do the inverse. So I'm going to show this as a fraction form. But when I see 2x, that technically means multiplication. So the opposite of multiplication is division, which means I'm also going to divide that side by 2. And that's going to give me x equals 5. And there is my solution. Now to show you again, if I were to plug this in, 2 times 5 minus 1. So if I plug it into the original equation, that'd be 10 minus 1, which equals 9. And again, that is what I'm looking for. I want my equation to equal 9. All right, so as we go through this, we're going to start to add some more pieces here. So in this next one, I have x plus 3 minus 2 equals negative 6. So if I put my line down where my equal sign is and separate, notice here on the left side, I have my expression x plus 3 minus 2. So sure, I can do inverse operations right away, but sometimes on an expression, the expression might not be completely simplified. What I mean by that is up here, x plus 2, that's simplified because those aren't like terms. 2x minus 1, that's simplified because those aren't like terms. Heck, even the 6 and the 9, those are simplified because you can't do anything with them. Now here, I have 3, positive 3, and minus 2. Those are like terms. So in this case, I might have to combine like terms before I do any sort of inverse operations. So if I take positive 3 and minus 2 and combine them, that would give me positive 1 instead. 3 minus 2 would give me 1. Now this side is simplified as much as possible, so now I can do my inverse operations by subtracting, and I would get x equals negative 6 minus 1. Those would combine to give me negative 7. So in this problem, we're going to check to simplify first. All right, last one here. I have 2x minus 3 plus 4x equals 9. So again, try and look to simplify, in this case, combining like terms. I have 2x, I have 4x. Those are like terms. Those would combine to give me 6x. Combine means add them as is. And then I would have my minus 3 still equals 9. Notice I didn't touch the 3 because that's not a like term, doesn't have x with it. Now I'm going to solve by doing inverse operations since we're simplified. So I'm going to add 3 first. That would give me 12 on the right side, but it's going to cancel out there. I'd bring down my 6x because I haven't touched that yet. And then lastly, to get rid of 6, I'm going to divide both sides by 6, so it cancels there, and I would get x equals 2 as my end result. Okay? Now again, what these mean, if I were to plug 2 back in where I see x, so if I plug it in there and there, I should get 9 as a result when I simplify that side. So again, looking at solving equations, simplifying first, and then trying to find a solution by doing inverse operations. All right, next we're going to add into this. You'll notice here in this problem we have ourselves some handy dandy nifty parentheses, right? So we have -3 parentheses x plus 2. So again, when I split up this equation into the left side and right side, rut-row spaghetti-o, I need to simplify first. Now in this case, I can't combine like terms, so it's not like the previous two problems, but instead what I want to do here, when I see parentheses, I want to distribute first at all times. I shouldn't say at all times. There are cases when we maybe don't need to distribute. There's different ways to solve these things. But the way you guys are probably used to when you see parentheses is distribute. So for example, I'm going to take and distribute that -3 throughout. Distribute means to pass along and to multiply. Because anytime you have a number in front of any sort of variable or any sort of bracket like a parentheses, it means we're multiplying by -3. So I would take -3 times x, which would combine to just give me -3x. -3 times 2 would give me -6. So I would write this as -3x minus 6, and that's going to equal 6 on the other side. So again, I'm multiplying. And again, when I multiply a number and a letter, I'm always going to write it next to it because that's how we show multiplication. And since we don't know what x is, we're just going to write it as 3x. Then to solve now, this is simplified because again, the 3x or -3x and the 6 are not like terms. So I can start doing inverse operations by adding 6 to both sides. Here would give me 12 there. That would cancel. It's going to give me 12 because they're both positive. Then I have -3x. And the last thing, this again means multiplication because we distributed. So that means I need to divide both sides by -3. That's going to give me x here. 12 divided by -3 is -4. Now some of you don't like to write it like this in backwards order, so if you want, I can just flip those right now as long as I don't change any of the signs. So I get x equals -4 as my solution. So I distribute to simplify. Next example, I'm going to have to distribute again. I see the -3 parentheses 1 plus 6r equals 14 minus r. I see the parentheses, think and distribute. Now the only thing I'm going to throw in here now is notice I got a 6r on the left side and an r on the right side. Ooh, so not only do I have to distribute, but I also have variables on both sides of my equation. So we'll talk about that in a second. But the first thing I want to do is distribute the -3 to those two terms. So -3 times 1 would give me -3. -3 times positive 6r. I'm going to multiply the numbers. So that would give me -18. 6 and 3 are 18. I'm going to make it negative because of the -3. And then I'm going to keep the r attached. And that's going to then equal the right side, which I haven't touched. Now, on both sides here, I have two expressions. Both of them have a number and a term with a variable. So a number and a term with a variable. So what I want to do here is when I have variables and numbers on both sides of my equation, what I want to do is combine my like terms on either side. Meaning I'm going to try and combine all of my variables to one side and all of my numbers to the other side. So I want to gather my variables either to the right or left and my numbers to the right or left. It doesn't matter how we do it. We're going to do it the opposite. So for example, if I see -3, this is one way to do it. If I see -3, I can add 3. Now by doing this, what I'm doing is I'm collecting my numbers on the right side. So 14 and 3 would give me 17. So I'm bringing my numbers to the right, which means I want to bring my variables to the left. So what I'm going to do here is I'm going to add r from the right side, and I'm going to bring it to the left side. So I'm going to still add my variables or do inverse operations like I would do with numbers, but now we're just trying to think about doing that with a variable, which is the same, it's just an unknown number. But again, what that does is cancel it on the right side, and that brings it over to the left side, and those would combine to give me -17r. So I brought my variables to the left side and my numbers to the right side, and now I can simplify this equation or solve this equation by simply doing inverse operations. So in this case, I'm going to divide both sides by -17. That's going to cancel on the left side, leave me with just r, and on the right side, those would divide to give me -1. Okay, so we looked at distributing as well as gathering your terms on the same side when you have variables on both sides of your equation. All right, these next two examples are a little sassier, a lot more involved. There's going to have all the pieces involved. So what I want you to do is try this one on your own. We talked about inverse operations. We talked about simplifying by combining like terms. We talked about distributing and also what to do with variables on both sides. So in these last two examples, Try this out. You got a lot of things going on, so pause the video, give these two a shot. All right, so this first example, a lot of meat and potatoes. I didn't touch this left side. That's simplified as much as possible. I just brought it down. Distributed first to get 42. They're both negative, so it becomes positive. And then negative 56n, because that's a negative 7, positive 8. Then I combined my like terms. Then I brought and combined my variables and numbers to either side. So I took my n's and brought them to the left, and my numbers and brought them to the right. I then got 61, n equals 61. Then using inverse operations, got n equals 1. Had to distribute on both sides here, then combine my like terms, and then I gathered my variables and my numbers on one side, and I paused here because I have 20 n equals 0. Good little teaching point here. 0 is a number, folks, okay? So just because everything over there would drop out and essentially go bye-bye, that doesn't mean, and what this is a common mistake, doesn't mean that it can't be solved. It just means now that when I divide by 20, n is going to equal 0. 0, folks, understand that 0 is a number. If you were to ask me right now, how many cats do you have at home, Mr. Waz? Well, guess what? I have 0 cats, okay? That's not no solution. It just means that 0 is a number. I have no cats, just like I don't have birds. Okay? All right. Last two problems here, folks, some special cases. So again, with the solving, I'm just going to go through this real quick. So if I again distribute, I'm going to get my 3x minus 6 equals 3x minus 6. Hopefully you guys will recognize something right away, but these are special cases because sometimes when we solve, and here when I get to the point where I'm going to gather my like terms on either side. So let's say I gather my x's on one side and I gather my numbers to the other side. Okay, what's going to happen here is I get this. Whoop, everything cancels out and I get 0 equals 0. Okay, so this is a special case. Special case because the thing I'm trying to solve for x completely disappears from the equation. What I'm left with is a statement. This is called an identity. Okay, so 0 equals 0. Now we're going to talk about what that means in just a second, but I want to show you the next problem as well so we can compare the two. All right, so here again, if I distribute both sides, I'm going to get 24k plus 12 times 11 is 132, and that's going to equal 24k plus 144. I know they're bigger numbers, whoopsie daisies. So now if I try and simplify this again, I'm going to gather my numbers. So let's say I subtract 132 from the other side, and at the same time I subtract 24k to that side. All right, the numbers here are going to cancel. They're going to, on the right side, they're going to combine. Here, those will cancel, but those will cancel out as well. So my variable cancels, I get 0, but on the right side, notice these numbers don't cancel out completely. They're actually going to combine to give me 12. So what I get here is 0 equals 12. So again, this is called an identity because all the variables are canceled out, and what you're left with is a statement here, 0 equals 0 and 0 equals 12. So if the identity is true, in this case 0 does equal 0, what this means is that we have infinitely many solutions. Now what does that mean? Symbolized IMS. It means that no matter what number I plug in for x, I can pick any number I want. The number 1, the number 20, 960, doesn't matter what I pick. Any number I plug in here will always work. Okay, so this works no matter what. This right here, when my numbers are not equal, this means that there is no solution, and that is the complete opposite of what I just said. There is no number I can plug in here that will ever work, so nothing would work. So these are some special cases that you will see as you're solving when things cancel out completely, and what you're left with is that identity that you then have to know whether it means that there's infinitely many solution or no. So a little review here on solving equations, folks. Good luck. If you got any questions, let me know. Otherwise, we'll see you next time.